When developers write code, they rely on functions to keep their logic organized. Instead of repeating the same lines over and over, they pack specific actions into reusable, modular blocks, following the principle of dry, don't repeat yourself. To understand how these blocks operate in memory, we have to look at the exact mechanics of a function call. When a program triggers a function, the main execution completely pauses its current state. It halts whatever it was doing and jumps to a completely separate block of code, isolating itself to perform one specific, dedicated task. This flowchart tracks that exact movement. We see program A traveling down a linear path until it pauses. Execution jumps over to function B, finishes the required task, and returns a value back to the starting point, unpausing the main program. Pause, jump, return. This rigid sequential cycle dictates the order of execution for virtually all standard software. But this strict order introduces a strange scenario. What happens if a function, while running its isolated task, is given instructions to call itself? On its face, this creates a logical paradox. A function pausing to call itself, which then pauses to call itself again, sounds like a blueprint for an inescapable infinite loop that would immediately freeze a machine. Yet, by intentionally triggering this self-referential loop, computers can solve massive, complex problems without crashing. The mechanism behind this is called recursion. We can observe recursion in action by taking on Practical 7 from the Python curriculum, finding the factorial of a number, like 5, using a recursive function. The function doesn't calculate the factorial of 5 all at once. Instead, it breaks the problem down. It calculates 5 multiplied by the factorial of 4. This diagram shows the immediate consequence of that logic. Because the function called another function, even though it called a version of itself, the primary rule still applies. The current state for factorial 5 must completely pause, waiting for an answer. This paused state, along with all of its local variables, is saved in a specific block of memory known as a stack frame. It sits at the very bottom of what we call the call stack. Now the descent begins. The new function call for 4 pauses to ask for 3. 3 pauses and asks for 2. With every new call, another frame is allocated in memory, building a tall tower of paused, waiting tasks. The computer isn't doing anything new here. It is simply taking the standard pause and jump rule and layering it repeatedly, constructing a deep vertical stack of suspended memory. If the function continues this descent indefinitely, calling itself into negative numbers, the memory stack will quickly overflow, triggering a fatal recursion error. To prevent the system from crashing, every recursive function requires a strict, hard-coded constraint, the base case. For our factorial problem, the math dictates a clear stopping condition. The sequence stops when the number reaches exactly 1. Looking at the top of our stack diagram, the base case behaves differently than all the frames below it. It does not trigger a new function call. It simply stops and returns a solid, unquestionable value of 1. Defining an airtight base case is the single lifeline you have. It is the only thing standing between a successful calculation and a destructive infinite loop. With a concrete answer finally in hand from the base case, the downward descent halts, the timeline reverses, and execution begins traveling back up the chain. In this visualization of the call stack, we see the pop mechanic in action. The topmost frame returns its confirmed answer to the paused frame immediately below it. Its task complete, the top block is destroyed, freeing up memory. This triggers a rapid chain reaction. The receiving frame unpauses, completes its multiplication, and passes its new total to the next frame down. The stack collapses, frame by frame. The process repeats until the stack completely empties. The very first original caller is finally unpaused, receiving the fully combined answer of 120. Recursion is effectively a structural illusion. The computer systematically shatters a problem into small pieces, suspends them in memory, and reassembles them using basic return mechanics. Developers rely on the recursive method because it allows them to write incredibly clean, short, and elegant code to process highly complex datasets. But that elegance comes with a strict engineering penalty known as call stack overhead. Every paused function in a recursive descent exists as a unique local variable. These execution frames take up physical space in the computer's memory. When an algorithm requires deep recursion, the memory cost compounds heavily, creating massive overhead for the machine. You are trading machine efficiency for human readability. Recursive programming buys elegant code at the direct expense of memory overhead. Beyond the technical syntax, recursion teaches a specific problem-solving mindset. It proves that you do not need to map out the entirety of a massive problem all at once to solve it. You only need two things. You must know how to take one single, repeatable step down, and you must define exactly where the bottom is. If you establish a solid base case and trust the strict laws of computing, you can take that step in the dark. The system's memory stock will carry the final answer back up to you.